Sine u. Wait a minute. Is that right?
Yep.
V is between 0 and 2 pi. See, the thing is, if you're using phi and theta, it's hard to get mixed up. But if we use u and v, it doesn't matter what you use. So you can do the whole thing and switch them all and switch your limits, and it's the same answer. So everyone is OK with that? Yep. All right. We did earlier the cross product. We did the magnitude of it, but see, this time we don't need the magnitude. So what is the cross product of those two? Okay, hold on. It's a vector, right? Cosine u. Right here?
Yeah, in the same direction.
Okay.
And then
Sine v sine squared u. And then
it's
cosine u sine u. Can I get a second on that? Anyone agree? Yes? Okay, good.
I thought it was cosine of v sine squared u.
Oh, shit. Okay. See, this is where I knew we would run into a problem. Hold on. Cosine v sine.
And then it was sine squared
I don't know.
sine.
Where? Where? This one? Cosine v? Okay. Is that good? Okay.
Yeah, that's it.
I hope that's good. All right, we're not going to work. We already did it. It's in your notes, right?
I mean, is that going to be wrong if it was?
Yeah, it will be wrong if it's not right. But do you want to go through and do the partials and cross them to be double sure? Okay. It's more really like this is just a method. Like what are we doing, right? Like what's the method here? So what we need to do now is we need to get the field and dot it with that vector. Dot products are easy to do, right? But what do we mean by the field? Well, here's your field. I need to dot that with this. But see, that has y, z, and x. This has u's and v's. We need it all in terms of u and v. So just like we did before, everywhere we see x, we replace with this. Where we see y, we replace this. And where we see z, we replace this. So this double integral right here becomes double integral over d. What is my vector field? It's y, which is sine v sine squared u. I'm going to run out of room. Let me just do it over here. Double integral d sine v sine squared u. Okay. Now z, cosine u. Oh, hold on. Oh, why didn't anyone catch that? Hold on. Yeesh. That would have been a disaster right there. This is x. This is y. This is z. All right. Sorry, the cross product was just for that second part, right? Okay. So this is sine. That would have been not fun after that, huh? Sine u cosine v is x. Shit. It must be too close to the end of the semester. What is this first component? Y, right? Which is sine u sine v. Then z. What's z? Cosine u. Then x. Sine u cosine v. I want to dot that with, I don't ever want to see that again. Goodbye. This right here. So cosine v sine squared u, sine v sine squared u, and cosine u sine u, if that's correct, dA. Now we can replace dA with du dv, dv du, and do our limits of integration because we know our restrictions on U and V, but I need to dot that, so I may as well dot it now. And I'll write my limits here. How about 0, 2 pi, 0 pi. All right, dot products. This times this. Sine cubed u, sine v, cosine v, plus this and this, sine squared u, cosine u, sine v, and then the last one plus sine squared u, cosine u, cosine v, d du dv. And then you get the pleasure of integrating that. If it doesn't clean up, does it at all clean up? Oh, are those two the same? Ah, they're so close.
Whoa, the last two are they're the same thing, right?
Cosine and sine.
Oh,
V.
didn't see that. Shoot.
Yeah. That's life, man. Let's see if I have this one worked out. Give me just a second. Is unit sphere y, x, z. Yeah, I don't have this one worked out. The book, example 4 in the book, they work out a problem very similar to this, but they use the vector field z, y, x instead. And, they get it to this point also. And once they get it here, they don't show much work either. You just kind of, but they show you what the answer is. You could do this now, right? I mean, given enough time, you could do that. I might go into three different integrals here. And in this first one, split my u's and my v's into 2 integrals and multiply them. And then in this one, split my u's and my v's and multiply them. Then over here, split my u's and v's and multiply them. Then just put them all together. All right, let's look at what's next. We have some special cases when we do flux. All right. There's nothing that says that when you compute the flux of something that the surface has to be closed. All right? Your surface does not have to be closed. If it's closed, then the orientation is easy to figure out, right? Like if I have the sphere, positive orientation is outward. But if I just give you like a sheet floating here in space, what's positive orientation? Right? So that's what these shortcuts are for. If I had that situation, would you agree that I could say z is some function of x and y? Right? If this is the ground down here, right? X, y, z. You've got some surface up there. Okay, if we have that, and our vector function has 3 components, p, q, and r, which, in the last problem, it was like y, z, x, or something like that. Whatever those are, we're calling p, q, and r. This will become this, which we already knew, except we're using x and y here instead of u and v. And when you do this cross product, you will get this. Now, this is kind of like, you remember we had the shortcuts where we had magnitude of the cross product? And it was square root of 1 plus partials and all that. This is that cross product before you square it. So if you do the cross product of these two, here's the shortcut. And look at this shortcut actually does the dot product for you. So what it will be is negative p times partial g with respect to x minus q times partial g with respect to y plus r. These are in your sheets that I gave you, right? What page is that on the sheets? Because this is a major thing to be able to reference.
Second to last sheet on that.
It's page 15?
Yeah.
Yeah, 14? Okay. Let me see what you have on here.
Yes, sir.
I only gave you one of those, huh?
Yeah, not all.
I didn't give you all of them. Okay, what I recommend you do is go to the notes I provided for this section online, because I have notes for all three special cases. All right? So it's this formula, and on the notes that I provide for you online, I know some of you I do not include this, so you might want to add this note in there. This is the formula, is if you're looking at your normals as pointing up out of the z-axis.
It's on
It is?
Yeah, pointing up.
Okay, it's on the handout I give you. It's on the notes up there too?
Yeah, pointing.
Oh, wow, I did update it. What the heck? Okay. Is that the CDF or is that the PDF? Okay, the PDF version does not have it. Yeah, the CDF is good. So if you're using the PDF, make sure you add this note to it. So let's just try and back up and try and figure out what this is saying. If we're trying to find the flux through a surface, and we're looking at the normal vectors as pointing upward, right? And our surface is a function of x and y, and normals are pointing upward. Then this is all we have to do. The double integral over the region D, which would be the shadow on the ground of this computation with respect to area. And we're done. Now, what happens if the normals that you have are pointing out the bottom, which will be the case sometimes? How do you think this formula changes? All the signs change. This becomes plus, plus, minus. And that's it. All right? Now, if we have a special case where our surface can be written as a function of y and z. So this time, your surface is out here like this, you know, and your shadow is going to lie onto the yz plane. Understand? This is our domain on the ground. Then x is a function of y and z. Then you don't have to go through all this mess of coming up with the formulas and crossing them. This is it right here. As long as you treat the normals as the ones pointed out towards you, okay, like out towards us. If you want to make your normals go into the page or towards the negative direction of the x-axis, then these will all change again. Negative, plus, plus. All right? And then finally, if your surface can be expressed as y equals a function of x and z, that's like this. Here's my surface this way. Then normals, which way? Out the right. Here's the formula. Is that what I have on my CDF? Out the right. I think on the PDF I don't say anything. And it's opposite on the PDF, isn't it? On the PDF version, doesn't say positive, negative, positive? Yeah. Yes? Okay, so if you're going to stick with the PDF version, that's your normals pointing out the left. This is what you have when the normals point out the right. Does this make sense or not? Use this formula right here if you want your normals pointing this way. If you want the normals to point out the left, switch the signs. That's what's in the PDF. I have 6 minutes. I think I have enough time to do one. At least set it up. Find the flux of the vector field. There's your vector field. This is, the surface is the part of the paraboloid z equals 4 minus x squared minus y squared that lies above this region. So it's giving me this paraboloid. Okay, its region, if we look at it straight down, the region on the ground, right, is a rectangle. And that is a function of x and y, isn't it? So this is g of xy. This is p, what? qr, right there, right? And since it is a function of x and y, I can use a shortcut. It's telling me to use upward orientation for the normal vectors. So I want to imagine my normals are coming up here. So that means I can use the formula directly the way it appeared in the notes, which is this first one, right? I'm going to do double integral over d of negative p. Yeah, if the normals are pointing upward out the z-axis, right, upward, times partial g with respect to x minus q times partial g with respect to y plus r dA, which will be equal to double integral over d. What's negative p? Negative p. Negative xy times partial of g with respect to x. What's the partial of, I'm sorry, I'm a little off here. Here's my g. What's my partial of g with respect to x? What's that? Negative 2x. Okay. Now, negative q. What's negative q? Negative yz times partial of g with respect to y, negative 2y, and then plus r plus zx. Got it? dA. Now, my region D on the ground is given to me by this restriction. So I knew that on the ground, x, y, I was inside this box, right? That's D. So I'm going to have d what over here? dx, dy, or dy, dx. It won't matter, right?
You would plug in 4 minus x squared minus y squared?
Yeah, okay, so look, what we have to look at now is if I'm going to be integrating with respect to x and y, I need all these to be x's and y's in here, right? I have a z in here, but z is 4 minus x squared minus y squared, and that z right there is 4 minus x squared minus y squared. So I'm almost done setting it up. Integral 0 to 1, 0 to 1 of negative xy. I can actually put those together. What's that? 2x squared y. This one plus 2y squared z, but z is 4 minus x squared minus y squared. And then last one plus x times 4 minus x squared minus y squared. dy dx. There it is.
This can happen.
This turns out to be 713 over 180. You would just distribute all this out, right? Multiply it all out, and then it's just pretty simple integration at that point. All right, so there's some more examples, of course, that I want to do. I'm not going to have time. I've got that one and that one. Now, just so you know, these two problems, example 5 and example 6, are actually out of your homework. They are problems where'd it go? 27 and 31, I believe. No, 27, 31. Yeah, I think that's 27 and 31. Here's what I'd like for you to do for homework for this. I pretty much have presented all the ideas. I haven't done enough examples yet. I will do these 2 examples when we start class next time. But I'm asking for homework that you look at problems 5 through 31, odds. And this is off of page 817. Now that's a lot of problems right there. So if you want, what you can do is at least just get them set up, not grind out all the answers for them, and then go back later and try and get like the numerical result. Like just get to the integral. All right, and if you want to know if you got it right or set it up right, you can let me know. But if you get hung up, just realize I'm going to do a couple of more examples. See, we have some examples where we have to do flux on an object like this, where you've got 2 surfaces. So like if you look at this surface right here, you have some normals pointing this way and some normals pointing that way, and you have to adjust your formula for that. So I'd like for you to see me do that before you try it, but it's well within the ability of some of you in here to do that, to try it. So, all right, next class, finish it up. 2 sections left.